Hello, we are working on Chapter 9, Intro to Differential Equations, and this is section 9.2, and we'll be talking about slope fields and lead up to an approximation technique to solve differential equations via an approximation method, and that method is called Euler's method. So what is a slope field? Well, first off, so far we have been studying first order differential equations. And remember what a first order differential equation is. It is an equation that whose highest derivative in that equation is the first derivative. Therefore, you see first order. And we've gone over one technique of solving a differential equation, a first order one, and that is using the separation of variables. But sometimes it's not always possible to separate the variables and follow that technique. There are other methods to find solutions to differential equations exactly, but of course there are many differential equations out there that you cannot solve. But there's still hope in using an approximation method that we can at least come up with an idea of what the graph of a solution would look like to an equation that is not solvable. And one way to do that is via a slope field. So what is a slope field? Well, literally, it's a field of slopes. So we return to the classic concept of calculus, which is the first derivative that represents the slope of the tangent line of a function at particular points in the curve. So if we've got an expression for dy dx, let's suppose dy dx is an expression in variables x and y, we can create a slope field which looks like this graph in blue over here on the right. Notice that we've got little lines everywhere. What we would do is we would take our equation dy dx equal to f of xy, and we would identify, let's say for instance this is a point, let's say if this point is the point 0, 1, we would take the x value of 0, the y value of 1, and we would plug in, and in this case they're generating a slope field using the y prime equal to x plus y. So if y prime here is equal to x plus y at that particular point 0, 1, we would say this is 0 plus 1, and we would say that our slope of the tangent line of our solution to our function is going to be equal to 1. And we have the point, we have the slope, and we can go in and right at that point just draw a tiny little slope or a tiny little tangent line. And you can see the xy plane has an uncountable number of points, ordered pairs x, y. So you have some options of how many points do you want to put on the slope field. You also want to be relatively uniform, just like you would in creating points on horizontally. You'd want to evenly space them out, right? That might be 1/2. This is 1. This is 2. You would want to also in the plane create a grid and say maybe this is 1, this is 2, this is 3. And you want to identify just how dense do you want your slope field to be, and that will determine how many calculations you need to make. It is quite cumbersome to go through many times creating individual little mini tangent lines, so there are several applications out on the internet called slope field generators, and let's look at one so that you can see the concept of identifying particular solutions to a differential equation. So I have one, and I'm going to stop and open up. This is a slope field plotter or slope field generator put out by GeoGebra.org. And I'm going to start with in here, I guess I should leave that there. You can see f prime of x comma y equal to cosine x. So I'm saying that the derivative dy dx is equal to cosine x. Now we know we can separate our variables here, and we would end up with f of x would equal sine x plus c. So it would be a family of functions of sine. You can create, you can modify in here the range of values for x and y if you'd like. You can increase the density of your slope field. That means that, they're creating more little tiny slopes, which is kind of nice. And what this slope field represents is the entire family of solutions. It's the general solution to the differential equation that was listed there. So now I'm going to pick an initial value, and I'm going to just click on solution A, and notice my initial value, I said let f of 0 equal 0 for let y of 0 equal 0. And if I start that, you can classically see that this is the sine function. You can see right here at 3.14 at pi, our sine function is equal to 0. You can see that at sine of pi over 2, which is about 1.5, our output is 1. So you can see that that is the sine function. Also, if you scroll in here, we have the understanding that the slope field, your solution, based on the initial value that you start with, you would navigate through the slope field by starting off with the slope of the tangent at the initial point, and then after a while, as you move forward to the next one, you would change its direction. So you can see as you're going through, as you're navigating through the slope field, as soon as you get to another tangent line, you want your graph to be that tangent line. You want it to be, your curve needs to be on that, or that tangent line should be on your curve. And we can click on different ones. So if I started with 0, 1, you can see that this is just a vertical translation of that sine curve. So hopefully that creates some understanding of the usefulness of a slope field based on initial conditions. And what's useful about the solution to the differential equation is if you have an idea of its shape, then you have ideas of its you can estimate particular outputs at a point, which leads us back to an estimation technique that many physicists may use without having to solve their differential equation. So I'm going to step out of this and go back into our worksheet, and I'm going to create a page here, and I'm going to introduce the concept of Euler's method. Okay, so Euler's method is used to approximate specific outputs for the solution to a first order linear differential equation. Okay, so the idea behind this is exactly what we just did. If you start with an initial value and you follow along on the tangent line, and then after a particular time, you would change course using the next tangent line, because you know that your graph is going to be changing direction and changing its derivative or its tangent line out, or slope of the tangent line at particular points, and you kind of navigate through that slope field. So if we start with an initial point in the plane, and we call that x sub 0, y sub 0, and we identify a step size. In other words, we want a uniform slope field, and we identify what is known as a step size, h. So in other words, as we move along the x-axis, we would stop at a particular point, let's say, and it would be uniform. So in other words, if we had x sub 0 equal to the x sub 0, then x sub 1 is going to be x sub 0 plus that step size, and x sub 2 is going to be x sub 1 plus that particular step size, so that we would stop at consistent intervals and change direction. Then, if we're starting off with our initial point and we identify the step size and we are given a dy dx of a particular expression in x and y, this dy dx represents the slope of the curve, or a slope of the tangent line at a particular point, right? So we start making equations of those tangent lines. So if we are given, if we start with x sub 0 and y sub 0, and we have slope f of x sub 0, y sub 0, because that would be the slope at that particular point, then the equation of the tangent line is going to be y minus y sub 0 equal to f of x sub 0 times of x sub 0, y sub 0 times x minus x sub 0, right? And we can then at the next point, we would stop after a step size. So we would move along this line until we get to x sub 1, y sub 1, to the very next one. And we know that x sub 1 is going to be x sub 0 plus h times y sub 1. And at that point will still be on that equation of the tangent line, but now we want to switch direction. And what do I mean by switch direction? We want to calculate a new slope and then proceed to the next step. So we know, since it's on this tangent line, we can say that y1 minus y sub 0 is equal to f of x sub 0, y sub 0 times x sub 1 minus y sub 0. So all I did from the above equation was, I know that my point x1, y1 is also on this line, so I know that it satisfies this equation. Well, now I'm just going to play around with some algebra here, and I'm going to say y1 here is going to be y sub 0 plus f of x sub 0, y sub 0 times, and what is x sub 1? X sub 1 we know is just h more than the previous x value. And then I'm going to subtract, up here this should be x sub 0 and not y sub 0. And I see in this algebraic expression that x sub 0 cancels with the minus x sub 0 to just leave h. So now I've come up with a formula to calculate what y sub 1 is. It's just going to be the previous y sub 0 plus our derivative evaluated at the previous point, but then times the step size, h. And now I would I would start again with x sub 1, y sub 1. and its slope, f of x sub 1, y sub 1, would be the slope, or the new slope, right? And then the new equation would be y minus y sub 1 equal to f of x sub 1, y sub 1 times x minus x sub 1. And I would move my graph along, move along this tangent line until the next step, right? And that next step is going to be our x2, y2, and we know that x2 is going to be x1 plus h. And what is our output of y2 going to be at that step? And again, we would plug in these values. It would still be on the tangent line. This point is on the tangent line. And so again, we'd be repeating the same process. Our variable y would be, we'd have y2 minus y1 equal to f of x1, y1 times, and our x would be x1 plus h, or that x2 minus x1, but our x2 would be x1 plus h, and we'd have minus x1. Again, we would be able to cancel out our x1 minus x1 because that is 0, and if we solved for y2, we would end up with y2 equal to y1 plus, and we'd still have h, and we'd have f of x1, y1. Good. I'm going to add a page here. And so in general, if you start with x sub 0, y sub 0, and step size h, right? We can approximate values for the solution of the initial value problem, right, with step size. So this means that x sub n plus 1 is going to be the previous one plus h, right? That, and given y prime or dy dx equal to f of xy, we can approximate values for the solution. So we can approximate an output. We know that y sub n is going to be the previous value, right, of y sub n plus h times x of the previous value, right? And n here would start with 1. Good. So, and keeping in mind that, well, we should probably do an example so that you understand how to use the formula. So you don't have to, this is just the derivation of the Euler's method, right? So this is Euler's method. To approximate outputs, values of the solution. To what? This is the solution. So y sub n